So in homework 3, we finally make the transition from our one-dimensional universe where we can only move one way or the other way. We did it horizontally first, then we did it vertically, but we've never had anything moving in 2 dimensions simultaneously. So we're going to finally make the transition from 1 dimension to 2 dimensions and higher. And we're going to find that our time is well spent in 1 dimension because it turns out that you can think of a 2-dimensional system as 2 one-dimensional problems. If you've been wondering why I've been having you put x and y subscripts on everything, it's because they're going to be both of them now and you don't want to get them mixed up. So let's examine what are the differences, 1 dimension and 2 dimensions. Well, in 1 dimension, let's say we had this being our 1 dimension, you can say plus and you can say minus. That is sufficient for describing direction because in 1 dimension there's only 2 things you can do. That's not going to work anymore. So let's say I have 2 dimensions like this. If you just say plus, first of all, is that plus x or plus y, right? Plus and minus don't make sense anymore. And you also have a bunch of other directions, right? What about this, or this, or that? So we go from having 2 possible directions in 1 dimension. How many possible directions are there in 2 dimensions? An infinite number, okay? No matter how closely 2 things point, if they're not exactly in the same direction, I can always squeeze one in between. There's an infinite number of directions that are possible in 2 dimensions. So clearly plus or minus is going to have to go out the door. We're going to need a better way of talking about vectors in 2 dimensions and higher. So let's talk about that. There's 2 methods. Method 1 is called the size and direction method. If you've seen this in math class, you may have also heard this called the polar notation. I just call it size and direction. So let me remind you, when you have a vector, the 2 pieces of information that a vector carries is how big is it and what direction does it point. And the easiest way that I can say what is the vector is to say, here's the size, here's the direction. I'm basically giving you a package of those 2 pieces of information. Let me give you an example. So let's say I have a velocity vector. Could be any vector, I'm just picking on velocity. So I'm going to say, how big is it? Well, it's 5 meters per second as an example. And now I can't just say it's plus or minus. I'm going to actually have to give some kind of reference. Let me go ahead and say that there's a horizontal line here. Let me say that this angle is 30 degrees. And let me say that my x and y axes look like this. So I'm just using these standard x and y axes that you probably have used mostly. And here's how I'm going to describe this vector. I'm going to say this vector is 5 meters per second, and that's its size. And then I'm going to separate with a comma a description of direction that is sufficiently unambiguous that even though there's an infinite number of possible directions, that someone knows what I'm saying. So here's what I'm going to say. This vector does not point along the plus x direction. It points, think of it as the hands of a clock, right? Imagine the tail of the vector kind of getting rotated. It's going to be 30 degrees counterclockwise from there, right? So 30 degrees counterclockwise from the plus x axis. That is the direction. If you don't normally use those abbreviations, I would write them down, CW and CCW for clockwise and counterclockwise. Okay, counterclockwise is an extremely long word to write out longhand. Okay, so you can see that the spirit is still there, right? Here's a vector, here's a size, here's this direction. In one dimension, we might have written something like this, plus 5 meters per second, right? And that was okay in one dimension, because here was the size part, right? And here's the direction part. But that made sense when plus and minus was completely sufficient for two possible directions. Now, the direction, instead of being a plus or minus sign in the front, is this huge long sentence fragment in the back, because you need that much more kind of flowery description to say what is the direction when there are an infinity of directions that are possible. Okay? Now, I should also say that when you're expressing directions, there is multiple ways to do it. For instance, you could instead say this arrow is not pointed in the plus y direction. It's right? Rotate like hands of a clock. It's going to be clockwise from there by how much? 60 degrees. So you could say 60 degrees clockwise from the plus y axis. There's nothing wrong with that. It's exactly the same direction, just from a different reference. If you are willing to use an angle that was greater than 90 degrees, you could reference it from the minus x-axis or minus y-axis. And there's nothing wrong with that too. My general preference is, let's use whatever axis is close by so we can at least keep the angle less than 90, right? And I don't particularly care if you're referencing from the minus x-axis or the minus y-axis. Just, I like to keep it to whatever is close by so that we can keep the angle under 90. But if you like to reference it from some far away axis and want to use an angle greater than 90, there's nothing wrong with that either. Okay? Now, this method has advantages and disadvantages. The advantage, of course, it's literally in the spirit of what a vector is. Here's how big it is, here's the direction. But the disadvantage is that's not very computationally handy, right? It's basically almost a sentence, right? Well, how am I going to plug that into an equation? So, the second method, which is the other method, has exactly the opposite strengths. It's a more obscure way of saying what the vector is, but it's ready to plug into equations. So, I'm going to show you that second method now. Are there any questions before I do that? Okay, so let me show you the second method. This is called components. Method 2, components. So this is a way of recognizing that a vector can be broken down into pieces, or we call these pieces components, right? It's like stereo components, right? You have the different parts of your stereo which form to make your stereo, right? You have your receiver, you have your antenna, you have your speakers, right? So I'm going to take a look at this arrow, and I'm going to make some decisions. Now this arrow is diagonal relative to these axes, right? It doesn't point along either axis exclusively. So the x-axis is horizontal, plus x points toward the window, and minus x points toward the door, right? Okay. So if you had to make a judgment call about this vector, does it point more towards the window or the door? The window. So if I had to draw how far does this go toward the window, it's that much, right? Okay. Now as far as the plus y direction, okay, plus y, in my case, is toward the ceiling, minus y is toward the floor. If you had to make a judgment call if this points more towards the ceiling or the floor, which way does it point? Ceiling. So there's a part of this that points toward the ceiling. These are the two components of this vector. So we call this the x component because it's the component that lies along the x-axis. It's how much that vector points along that axis. And this is the y component. Those are the two pieces. And if you're noticing that the x and y subscripts are familiar things, and why I started to have you do them, it's because it was in preparation for the fact that when we talk about the v sub x, that might not just be the velocity along the x direction of something that's moving only along the x direction. That may be the x part of a bigger motion. And same thing with the y component. We started using vy because it was good habit for when the vy may not just be the all of the velocity, it may be a part of a greater velocity. Okay? So you can notice I kind of snuck it in, right? So at some point I said, hey, why don't we call this this? Right? It was in preparation for taking our one-dimensional world and realizing that what's going on in the x direction may be just a part of what's going on in the greater world. It may also have something going on in the y direction too. In general, a velocity can have both pieces, right? So let's find out about these components. Now here is the beauty of components, and here is the beauty of why we spent so much time in one dimension with it going and having a big payoff. Now an x component by definition is along the x-axis, which means that it can only point one way or the other way. So on the x component, it can either be along the plus x or minus x. So is our x component pointed on the plus x or minus x? Plus. So even though we're not allowed to use the plus or minus anymore for the whole vector, we can still salvage all those skills that we learned in describing the components of it. Okay? Remember that the direction of the vector as a whole is not plus or minus. It's 30 degrees blah, 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 right? But the x component is plus. Look at the y component. The y component can only point one of two ways. It can point with the plus y direction or opposite. Do we have a plus or minus y component? Plus. It can be plus. So the strategy we used for the entire vector before, we can use it now, but just for the components, not for the vector as a whole anymore, just the parts of the vector. Okay. And I guess I first should write down, in case it isn't clear, this is a right triangle, of course. Now if we have a right triangle, we can also put down how large are those components relative to the whole hypotenuse, right? And so this is where SOHCAHTOA comes in. So SOHCAHTOA. This is probably the highest level of math that we expect you to be comfortable with, and so I'm going to briefly review it and then expect that if you need some brushing up, you'll use the resources that I posted. Now, I am interested in figuring out the size of those components, and I also know the sign of the hypotenuse, or I know the size of the hypotenuse, right? So I'm going to be interested in sine and cosine. Because again, the hypotenuse is known, right? And I want to find the opposite and adjacent sides of my triangle. Now just as, again, a super quick review, which one's the hypotenuse? The hypotenuse is the longest side. It's opposite from the right angle. Which one's the adjacent side? The adjacent side is adjacent to the angle, not including the hypotenuse, because that's already taken. And the opposite side is opposite the angle that's labeled. Is this all, like, familiar from math class? Okay, you know how to identify this. Okay, so let's say, I don't know, cosine first. Cosine of theta is equal to adjacent over hypotenuse. Okay, that's the ka in SOHCAHTOA. And that's, of course, always true. That's the definition of cosine. In this particular case, which side is the adjacent side again? Vx. And then I'm going to, and then the hypotenuse is, of course, the whole thing, right? Which I guess I'll just call V. And so this is just in this case. So in this particular case, those are the things that the adjacent and hypotenuse happen to be, right? So here's what I'm going to do. I'm going to solve for Vx. Vx is equal to V cos theta. And the other thing that you should be aware of, I'll put some kind of ghost absolute value signs here. SOHCAHTOA does right triangles. SOHCAHTOA does not do triangles with arrowheads on every side, which they should have. So really what you're getting with SOHCAHTOA is how long is the side. We've decided separately, of course, that it should be plus because the arrowhead points to the right. So this is V cos theta. If you want to put in numbers, that is plus 5 meters per second times cosine of 30. And that, plug and chugged further, is plus 4.33 meters per second. Rounded off a little bit. Now, you can work out separately with the SO part of SOHCAHTOA that the y component is going to be the hypotenuse times sine of theta. And again, we decided separately that it's plus, and SOHCAHTOA supplied the size of that component. That is going to be plus 5 meters per second times sine of 30, which works out to be plus 2.5 meters per second. Okay? Now, if you're not super comfortable with SOHCAHTOA at this point, do your very, very best to get super, super solid on it by the first exam. If you're not super solid on this, it's going to haunt you in the first exam and then continuously throughout Physics 1 and then all throughout Physics 2. Okay? So if you need at first to work out all this business like this, longhand, and work it out, okay, get to the point where you can look at this and just basically write this down and write this down, okay? So go, okay, got it. Both components are positive. I can see that. Adjacent side gets cosines, hypotenuse times cosine, and the opposite side gets hypotenuse times sine, okay? So just that quick. Get really comfortable with this, okay? And so that's the components method. The components method is, if you want to state the vector, what you do is you give it in terms of components. You say that it has this much velocity in the x direction and this much velocity in the y direction. So basically, it's taking something that's one velocity and breaking it apart into two easy-to-use pieces. But it is weird. It's like giving somebody a gift that they have to assemble, okay? So it's something that's in two pieces, which is really one thing, right? And of course, if someone gives you components, they have to also tell you what x and y axes are they using, okay? So x and y, of course, as we learned, is in the eye of the beholder. One of the things you can do to practice this, especially perhaps after homework 3, when you've done more simple stuff, or you can use it before. On the course webpage, there's a Math Skills Review link. And if you click on that, at the very bottom, there's a PDF worksheet of, I think it's called Vector Practice. And it has like a whole page. I think there's 9 or 12 different things where you can practice this. You can practice taking vectors apart into components, and you can also practice reassembling them, which is what I'm going to show you next. Okay? And they're rated into easy, medium, and hard. So the easy ones you should be able to knock off straight away. Maybe some of the medium and or hard ones you should revisit perhaps after the homework. Those give you some really weird looking axes to break it apart, or some other weirdness that makes it a little challenging. Okay? We certainly by no means will always use these standard x and y axes. In fact, the days of always using this are very numbered. We'll use some very strange x and y axes. Sometimes we'll go like this, x and y like that. Sometimes we'll go like this. Okay? And by the way, the easy trick for that, you guys have an advantage I don't on the whiteboard. You can always rotate your paper to make the x and y axes look however you want. Do your drawings, then turn it back. Okay? Okay. So, we've noticed that there's strengths and weaknesses. This size and direction notation is very straightforward, but it's not very handy. These are ready to plug and chug. So let's write down those two methods. So you have the size and direction method, and you have the components method. And because they both have their strengths and weaknesses, you want to be able to go back and forth between these two pretty much as you need. A lot of times at the beginning of a problem, you'll be given something in terms of size and direction, and you'll want to get it in the components to do a computation with it. Now, how do you do that? Well, I kind of inadvertently showed you how to do that just by showing you what components are. What you're going to need is you're going to need to decide plus and minus. So you set your axes, and then you decide what plus or minus is. And then you're also going to need sine and cosine, because the sine and cosine are going to allow you to express the two legs of your right triangle in terms of your hypotenuse. And then, oh, the other thing I forgot to show you guys, I pointed out that you could also do 60 degrees, right? So let's say, you might ask, how did I know to go over first and then up? How did I know to put the x component first and then the y component second? Well, it doesn't really matter. I did that simply because I wanted to entrap the given angle in my triangle. Is there something wrong with doing this, 5 meters per second, and doing the 60 degrees from here? Absolutely not. Then, probably, you would put this component first. Which component is that if I'm using the same axes? It's the y component. And then I'd put this one. That's the x component. The y component was positive before. Is it positive now? Yeah, it's still positive. And x component is still positive too. Nothing's changed. If this is diagonally rightward and upward, well, it's also diagonally upward and rightward. It doesn't matter, right? Doesn't matter which piece you put first. Just as a word of warning, though, which side of the triangle is this? Is this the adjacent side or the opposite side? Adjacent. Adjacent gets cosine or sine. Gets cosine. So this is going to be v times cosine of 60. All right. This is now the opposite side, so that's going to get sine, right? The sine of 60. So that's something that I really want to emphasize, and I think that when people do too many SOHCAHTOA problems in a certain orientation, they start to make connections that aren't there. Cosine always goes with the adjacent side, okay? It's like peanut butter and jelly, okay? They're always together. But the adjacent side, it really depends on your setup whether the adjacent is the x or the y. And I want to point out that when I broke it up the first time, the cosine, right, went with the adjacent side, which happened to be the x. The cosine went with the adjacent side over here, and it happened to be y. Okay? So don't always get the sense that cosine goes with x. It does not. Cosine always goes with the adjacent side. The adjacent side may be x and may be y. It depends on how you set it up. Likewise, the sine always goes with the opposite side. That could be x or y. It depends on your setup. Okay? So that's, you got to be really careful, and especially we will choose some weird axes. So you want to get that cosine sticking with the adjacent side like glue. Okay, sine goes with the opposite side. Now, if you're questioning whether these are really the same thing, let me point out that whether you break it apart as going up first then over, or over first then up, this is a rectangle, right? If it's a rectangle, which means that it's got to come out to be the same, right? This is the same as this. This is the same as this. And in fact, you will find that. The cosine of 60 is the same as the sine of 30. Try it on your calculator if you don't believe me. Okay, that's the general property of sines. So whether you choose it as cosine of 60 or sine of 30, it doesn't matter. It'll come out to be the same number ultimately. Okay. So you should never worry about, should I break it up in one way versus another? Do either way. The only reason I decided to go in this order, over first, then up, is because the angle was labeled there, so I wanted to surround my angle with my right triangle. Otherwise, I would have had to subtract 90 from 30, and maybe I'll make a mistake, right? I would make a mistake doing something like that, okay? So that's the essence of components. I guess before I even show you the reverse conversion, let me just do a few more examples. This is a skill that is really, really important. If you don't get the hang of it, it's really bad. Basically, if you don't get the hang of it, I think you can pretty much top out at a C in the class. Let's do another one. Let's say I have, and again, there's a whole practice sheet of these, but let me do another one real quick. Let's say it points like this. I'll have, I don't know, this is my velocity vector, 10 meters per second. And let me give the angle from here, 20 degrees. All right. Let's go ahead and set our axes like that for now. Let's not get them too crazy yet. All right. So that's a vector which I would call diagonally right and down. Okay. So it points more to the right. It points more toward the window than to the door. Right? It points more toward the floor than the ceiling. So I'm going to draw those two components, and I'm going to draw them like this, just simply because that's where the angle is given. So it's down first, then over. If you wanted to go over first, then down, that's fine. But you'd have to use 80 degrees instead of, see, I just did it, 70 degrees. 70 degrees instead of 20, right? Okay, which component is this one? It's the y. Is it plus or minus? It's minus. Okay. This must be the x. Is that plus or minus? Plus. This has a minus y component and a positive x component. Is the vector as a whole, is it plus or minus? You can't use it. You can't use plus or minus for the hypotenuse, remember? It's for the components. It's not for the whole thing. The whole vector is 20 degrees counterclockwise from the minus y-axis. Plus and minus is only for components, right? If you want to talk about the direction of the vector as a whole, you're going to need to describe it. So, is this the adjacent side or the opposite side of the triangle? It's the adjacent, so that gets cosine or sine. Cosine, so that's minus 10 cosine of 20. This is going to be the opposite side. It's going to get the sine. Okay. So that's the basic idea. To be able to take a vector that's diagonal and give it in terms of pieces. Make sure you correctly identify the plus and minus. Right? That's one thing we were talking about right here. And then assign which one is the sine and cosine properly as well. Okay. So that's the main goal of homework 3, or the most important goal of homework 3 is, can you get that straight? Now, the next order of business is that if someone just hands you components, can you reassemble them? So let me give you an example. Let's say that someone gives you a velocity vector, and again, I don't know why I'm picking on velocity, because this is true of any vector. And someone gives you these components, plus 10, minus 24.2. And they tell you that the axes they use were like this. So the question is, can you reassemble those to get the overall size of that velocity, and can you get the direction in terms of number of degrees from some nearby axis? So it looks like I'm going to have to pick that up next week. Just mainly in the next week or so, after you finish homework 2, see if you can get a little bit of practice with vectors. But I have not yet shown you how to reassemble components, so you might want to hold off on those.